Hello everyone, welcome to Manmaker. I am Ranjan Kumar and today we are going to discuss some communication system questions, important question we are going to discuss in a details. And this is for probationary engineer, BEL probationary engineer, electronics branch people and electrical branch people because this chapter is common in both the branches. Okay, as we have covered already communication classes about analog communication and digital communication, that we have covered already, that you can check in the previous classes. And today we are going to see some important and expected questions with detailed explanation and answer. Okay, and this is based on your exam pattern. All right, for PDF and more updates, you can join our Telegram channel or WhatsApp group channel. Here I am updating class notification, job notification, PDF, study material, whatever important things are there, you will get here only. Okay. And now you can access the Manmaker app from Google Play Store so that you can access your study material from this app. Okay. And I hope you are preparing well with this app material. You are covering all the things, important question, ebook, and all the things you are going to cover. So this is available in the Manmaker app. You can take from there. Okay. Okay. So we'll start as we have completed already all the things. So today we'll see how much what kind of level of question is there in the exam. So like that question we are going to discuss. Okay. Question number 1. In an AM system, if the modulation index is increased beyond 1, the transmitted spectrum contains. Okay. So AM, that is amplitude modulation. If we talk about modulation index, so generally modulation index we are denoting as a modulation index, that we are denoting as a mu, or you can say or small m, like that we are denoting this modulation index. Okay, so here it is written modulation index is increased beyond 1. That means this m, that is modulation index, is greater than 1. Okay, so whenever this modulation index is greater than 1, that time modulation is called as a over modulation. Over modulation. Okay, this is what over modulation. When this modulation index is less than 1, then modulation is called under modulation. Okay, under modulation. And when modulation index is 1, then it is called perfect modulation. Perfect modulation. Okay, so these 3 points are there related to your modulation index. So whenever this modulation index is greater than 1, okay, so whenever this is become greater than 1, then it will call over modulation, and it causes envelope distortion because the instantaneous modulating voltage exceeds the carrier amplitude. Okay, so it's what one kind of detection it will be present, that we call like in a envelope detection is there. All right, and due to this envelope detection, non-linearities will come. Okay, non-linearity will be present, which generate additional distortion component but not a harmonic. Okay, in the carrier side you will get distortion component, additional distortion component will be there, but harmonic will not present in the carrier side. Okay, so this will become in the spectrum, you will get one band will be there, or side band will be there, one carrier signal is there, and one you will get distortion. So you can say spectrum contains carrier, one carrier will be there, plus one sideband will be there, and one distortion product will be there. So from there you can say carrier plus sideband plus envelope distortion component. So option D is your right answer. So whenever modulation index is in a over modulation, that time the transmit spectrum contains carrier plus sideband plus distortion product, that is we called envelope distortion components. Okay, so from here option D is your right answer. Which is the sequence of PCM? PCM means what? PCM is a pulse code modulation. Okay, so generally when we are when in the class also we have covered PCM, pulse code modulation. That time I shown you the block diagram of pulse code modulation. In that block diagram, three main components are there. That is your what? That is your sampling. I told you in class also they will ask sampling, what sequence step you need to remember. So first it will go sampling, then quantization, okay, then encoding. Okay, so what, and in after that it will go to some like transmitter or regenerator, like that things are there in the block diagram. You can check there also. So sampling, what sampling will do, it will sample each analog signal or each analog continuous analog signal into a district level, okay, district level or digital level it will sample. Okay, after that it will go to quantization. So in quantization, that analog signal is converted in the each district level, district numerical level, okay. Or I told you it will take a rounding of value, okay, approx value it will take. When we are doing this thing, when we will do quantization, that time it will be like this. Our analog signal will be there. After that, it will going to do rounding of approx value, they will take off amplitude, okay. That part will be done by quantization, and this encoding is going to convert all quantized value in a digital code, you can say, or district code, like that. The process is PCM. So basically step is there. First it will go sample, it will do sampling using sampling theory. That time also we have read sampling theorem, that should be Fs is greater than equal to twice of Fm. This is the sampling theorem or Nyquist theorem we are saying. So by the following of this, they will do first sampling. After sampling, it will go for quantization. Then it will go for encoding. So your step will be first sampled, then quantization, then encoding. This thing you need to remember. Option D is your right answer. Okay. So okay, all right. Now from here, option D is your right answer, sampling, quantization, and encoding. Okay, now next one. Next question is what? In an AM system, the transmitted power increased by 50%. Okay, when modulation is applied. What is the modulation index? Okay, so here it's saying about transmitted power. So in AM, transmitted power means what? PT, that we are denoting by PT. This is what? Transmitted power. Okay, transmitted power, that is PT. PT equal to PC 1 plus modulation index by 2. This is the formula for transmitting power. PT is a transmitting power, PC is a carrier power, M is a modulation index. Okay, I will write here. PT is a transmitting power, okay, and PC is your carrier power, okay, M is a modulation index. Modulation index. All right. So now what is the question is transmitted power increased by 50%. So our transmitted power, that is PT, is increased by 50%. So we can say it will be 150% because it's increased, like percentage means 100 only, and now it is increased by 50%. So we can write 150%. Then PC it is not mentioned. So whenever in the question you will not get the value of PC, you should consider as a 1. Okay, then 1 plus mu or m, that modulation index only we need to find. So modulation index by 2, this is the like that we can write. Now this is what? 150 by 100. Okay, 150 by 100 equal to 1 plus m square 2. Okay, now here it will be you can write like this 150, and this is 1 plus m square by 2, and 1.50 minus 1 equal to m square by 2. We can take this one this side. Now 1 what? 1 minus 50 minus 1, this is equal to what? 0.50 equal to m square by 2. Or if you take 2 this side, if you take this to this side, then it will come 0.50 into 2 equal to m square. Okay, that is equal to 1 only, 1 dot something, 1 dot 0, that is mu square, and if you remove this square it will come root under 1 equal to m. So m is equal 1. So the value of 1 is the value of m, the value of modulation index is what? The value of modulation index is 1, 1.0 or 1 you can say. Okay, 1.0 or 1, same it is. So option D is your right answer. Okay, so when modulation index is equal to 1, it is called as a perfect modulation. Okay, perfect modulation. Like that, simple numerical you can also expect for the exam, that formula based. Okay, a tuned RF amplifier, a tuned RF amplifier improves selectivity by, okay, tuned RF amplifier radio frequency amplified means what? A tuned RF amplifier is an amplifier designed to amplify radio frequency signal over a narrow band frequency using tuned circuit, or you can say resonant circuit in the load. Okay, and basically tuned circuit used LC circuit. LC circuit means uh, a tuned RF amplifier uses LC resonant circuit. LC means inductor plus capacitor as the load instead of a simple resistor. In the like load side, generally we are using load resistor, but here in the tuned amplifier, tuned RF amplifier, it's using LC resonant circuit, combination of L plus C, inductor and capacitor in a load side. Okay, so in that case we have formula also for frequency. That frequency we can say f naught equal to 1 by 2 pi root under LC. This is what f naught is, your frequency response. Okay, f naught is your frequency response. Okay, f naught is your frequency in response. And here they have asked about what? Selectivity. So there is a relationship between, some relationship is there, a relationship between your quality factor, that is Q factor, then bandwidth and this frequency response. That will be this quality factor or Q factor is equal to f naught by bandwidth. This you should note to remember, this one relationship between Q factor, bandwidth and frequency response in RC or LC, in resonant circuit you can say, or resonant circuit. Just remember relationship in resonant circuit. In resonant circuit, relationship between Q factor, bandwidth and frequency response is Q equal to frequency response by bandwidth. Okay, so this Q factor will determine selectivity. This Q factor determine selectivity. Okay, this will determine selectivity, and this for higher Q factor, if higher Q factor is there, then selectivity will be better. So you can say for higher Q factor, better selectivity. Okay, this is the things. For higher Q factor, selectivity will also, it is increase you can say, or it will be better. Okay, so from here you can say option number B is there. Increasing Q factor of tuned circuit. How RF amplifier improves selectivity? How it will improve selectivity? By increasing Q factor. If you increase Q factor in RF amplifier, then selectivity is also going to increase. Okay, so this option B is your right answer. Increase Q factor of tuned circuit. Okay, sometime in an exam also they will ask the relation between Q factor and frequency. Like, what is the relation between, in a tuned amplifier circuit or in a resonant circuit, what is the relationship between Q factor and frequency response? that time they will give some like it is directly proportional to each other, and it is inversely proportional, like that option will be there. So just remember, q factor is directly proportional to frequency response, and q factor is inversely proportional to bandwidth. This 2 point also you need to remember from this question. Okay, so this thing you need to remember. Okay, and from here, if q factor is high, selectivity will be also increase or also high. So option B is your right answer. RF amplifier improves selectivity by increasing the q factor of the tuned circuit. Option B is your right answer. Okay, a phase modulation signal has a modulation index proportional to phase modulation. If we talk about phase modulation, so in phase modulation, phase will vary. Okay, phase will vary according to message signal. Okay, so in a phase modulation, phase will vary according to message signal and amplitude. Amplitude and frequency will be constant. Okay, amplitude and frequency will be constant in the phase modulation. So the modulation index is proportional to both amplitude and the frequency. Okay, because it will be constant. So option C is your right answer. If it will be for FM, that is your frequency modulation. So in frequency modulation, frequency will vary according to message signal. Okay, and here your amplitude and phase will be constant. Okay, if it is about AM, that is amplitude modulation, so your amplitude will vary according to message signal. All right, and frequency and phase will be constant here. Okay, so if they will ask about FM, FM, then amplitude and phase will be answer. If they will ask for AM, then your frequency and phase will be answer. Like that you need to remember. P means phase constant and phase will be changed. F means frequency will be changed. A means amplitude will be changed. Like that you need to remember. Option C is your right answer. Okay. Now, which modulation has the highest noise immunity for equal average transmitted power? Okay, so like for what? For which modulation has the highest noise immunity? Okay, highest noise immunity. So here FM with large deviation is there. Okay, FM with large deviation is there, which having highest noise immunity because it uses free emphasis plus de-emphasis. Okay, so because of FM with large deviation uses free emphasis and de-emphasis, both it is using, so it will improve SNR, signal to noise ratio. Okay, if signal to noise ratio SNR is high here, SNR is due to this SNR is high, so it will be register more noise, means less noise will be present here. So highest, you can say highest noise immunity immunity. Okay, due to this only it has highest noise immunity having FM with large deviation, because it uses pre-emphasis and de-emphasis. Okay, apart from that, you also need to remember one more thing, it having wide bandwidth in FM with large deviation. Okay, so from here option C is your right answer. Okay, a super heterodyne receiver uses high side injection. Okay, high side injection if RF is 120 megahertz and IF is 10.75 megahertz. LO frequency is, RF means radio frequency, IF means immediate frequency, LO means local oscillator frequency, that you need to find. Okay, so as we have discussed in the class super heterodyne receiver, that time I shown you diagram also. So it will be like that. Antenna will be there, then RF will be there, radio frequency. After that, one mixture is there. This is called mixture. Okay, and after that, IF will be there, intermediate frequency. Then we have one detector. Okay, then we have detector, then we have audio amplifier frequency, then output will be there as a speaker or anything. Okay, and here we have one local oscillator. This is what local oscillator. This is the diagram for super heterodyne this receiver. Super heterodyne receiver block diagram you need to remember till your interview. In interview also, so many times so many candidate got this question, draw a block diagram of super heterodyne. Okay, so now here you can say in super heterodyne receiver, generally this we will calculate IF. This is what IF, intermediate frequency. This RF is going this side, and local oscillator is also passing from mixture. So this IF, I sorry frequency of IF is equal to frequency of local oscillator minus frequency of radio frequency. This is the formula for a super heterodyne receiver. But here they have asked question for what, high side injection. Okay, so for high side injection, high side injection is equal to your FLO, local oscillator of frequency, equal to FRF. We need to calculate local oscillator. Okay, so local oscillator is equal to, we can write this is FRF minus, this will come this side, so sorry, plus, and this will be FIF. Okay, this we can write formula like that. For high side injection local oscillator we need to find. So we have RF is 120 megahertz plus IF we have 10.7 megahertz. Just we need to add this one. So 130.7 megahertz your local oscillator. Option B is your right answer. Okay. Suppose they have asked this question for low side injection. Okay, low side injection, if they are going to calculate for, they will ask for low side injection, so that will be your FLO, local oscillator. That time it will be minus FRF minus FIF. Okay, just remember these formula, high side injection and low side injection. In low side injection you need to do minus, and in high side injection you need to plus the RF frequency and the intermediate frequency. So from here 130.7 megahertz, option B is your right answer. Okay, the power spectrum density of white noise, the power spectrum density of white noise is 4 into 10 to the power minus 12. If the receiver bandwidth is 10 kilohertz, what is the noise power? We need to find the noise power. Okay, so noise power generally we will denote as a Pn, you can write, and this will be N node by B, where this N node is your power spectrum density, or you can say PSD, PSD of white noise. Okay, PSD of white noise. Okay, power spectrum density of white noise, and this B denote to bandwidth. Okay, bandwidth. Now this we have given this wala 4 into 10 to the power minus 12 into this we have 10 kilohertz, that is 10 into 10 to the power 3. Okay, now we can write here 4 into, this is minus 12, this is plus 1, this is plus 3. So 10, this will be 10 to the power 4. So minus 12 and plus 4, so 10 to the power minus 8. Okay, and we can write this thing 40 into 10 to the power minus 9, like that also we can write. And so this 10 to the power 9 means what? 40 nano watt. 10 to the power 9 is nano, so we can write option B, 40 nano watt is your answer. Okay, so like that, this is the basic, only basic formula you need to remember. Formula based, like that question you can expect. A super heterodyne receiver has RF, radio frequency, of 1 megahertz, and IF, that is intermediate frequency, equal to 455 kilohertz. What is an image frequency? Okay, image frequency. So image frequency we need to find. So image frequency, that will be your FIMG, you can write, equal to FRF, radio frequency, and plus twice of F intermediate frequency, IF. So this is the formula for image frequency in super heterodyne receiver. Super heterodyne receiver. Okay, so here everything is given. We have this one 1 megahertz. Okay, and plus this we are having 4 5, sorry, here 2 into 455 kilohertz. Okay, so option is in your megahertz, so let all thing we will make as a megahertz. So it will be 2 into, we can write 0.455 megahertz. Okay, and it will be 1 plus 2 into 0.455 is equal to 0.91 megahertz. All right, and this will be 1.91 megahertz. So option C is your right answer. Okay, so like that you need to use the formula and get the answer. Okay, now the next one is your, in digital communication, the purpose of channel coding. Digital communication, the purpose of channel coding. So in a digital communication, basically, like digital communication, what it will be do, like I told you at the time of introduction, is also in a simple line, it will convert analog signal into a digital signal. So basically, initially we have analog source as an input. Okay, as an input we have analog source, then it will go to source code. Okay, then it will go to source code, then it will go to channel encoding. Channel encoding. Okay, channel encoding, you can say. So basically, after that it will go to regenerator or transmitter, like that things are there in the block diagram. So what we have read there, first it will go analog signal, that will be in our analog form, then it will go to source code, there it is going to convert in a digital way. Then in channel encoding, what it will be do, it will detect error, and what, error only, it will detect and correct the error in the channel encoding by adding the retardance bit. Okay, so we can say it will improve bit error rate. Bit error rate, it will improve. Okay, BER means bit error rate. It will improve bit error rate. it will detect it will detect and correct the error by adding redundant bit, or by adding control redundancy to improve the bit error rate. Option C is your right answer. Okay, it will not remove it will not remove noise, it will not going to increase SNR, it will only improve BER, bit error rate. Okay, so option C is your right answer. In a delta modulation system, slope overload distortions occur when? So delta modulation, DM, that we have made in a class 1 table, there I shown the comparison of all kind of digital modulation, that PCM and PCM, DPCM, then delta modulation, and adaptive ADM, also adaptive delta modulation. So basically in that table you can check there. Delta modulation having two kind of noise. First one is your slope overload error, error or noise. Then another we have granular noise or distortion or error, you can say. So DM having delta modulation having this thing, and generally the slope of DM, generally the slope of delta modulation we are calculating as a step size, that is your del, or we can say sampling interval time. See, this del will called step size, and this is what sampling interval or sampling time you can say. Okay, so generally the slope of delta modulation we will calculate we will calculate as a step size. So whenever this step size, that is your del, or we can say del by ts, is less than your just a second, whenever this slope size is your, that is your del t of s, or sampling time is less than equal to delta of x of t divided by dt. This is the equation for a delta modulation. So whenever it is less than, or we can say this del is too small, okay, del is too small, then slope overload occur, okay. And when this del ts is greater than d of x of t by dt, that time our step size is too large, and that time granular noise will occur. Okay, so just remember, when step size is too small, then slope overload will occur, and when it is too large, then granular noise will occur. Okay, so here it's asked about slope overload distortion. So when it is going to occur, when the step size is too large. Okay, so this is the option A is, sorry, option B, too small. Okay, option B, if it is large, then it will granular noise will occur. But here they have asked about slope overload. So slope overload when step size is too small. So option B is your right answer. Okay, option B is your right answer. Okay, just point down both the points. In a PCM, that is pulse code modulation system, with a sampling rate of 20 kilohertz and the 10-bit quantizer, the minimum channel bandwidth required for. So sampling rate we have how much? Sampling rate we have given 20 kilohertz, and quantization bit we have, quantization bit we have how much? Quantization bit we have 10 bit only. Okay, 10 bits. And now we need to find the minimum channel bandwidth. Okay, so for minimum channel bandwidth we need to find first the rate. Okay, so rate we will find in PCM bit rate, that we are denoting with RB, is equal to N into Fs. Okay, N is what? Quantization bit, and Fs is what? Sampling rate. So N we have given 10, and this rate we have how much? 20 kilohertz. Okay, 20 kilohertz. So this we can say this is 10 and this is 20, so this will be your 200 kilohertz. Okay, 200 kilohertz, or we can write uh, fs we have it is given in what? Sampling rate we have 20 kilohertz. Okay, it is in frequency, So it will be we can write this one as a kilohertz as a 200 kbs, because we are calculating bit rate. So when we are going to calculate bit rate, the bit rate unit will be kilobit per second. Okay, so it will be 200 kilobit per second. Okay, so now we need to find what bandwidth requirement. So bandwidth is what? Bandwidth is your bit rate divided by 2. Bit rate we have 200 into, it is in kilo, so 200 into 10 to the power 3 divided by 2, so it will be become 100. Okay, so 100 into 10 to the power 3. Now we need to find bandwidth, so it will be the range of frequency, so it will be 100 kilo hertz. Okay, option C is your right answer from here. So option C, 100 kilo has your right answer. Okay. Okay, so like that question is there in your exam. Okay, like that question you need to prepare from this 500 important technical question which I gave you in app material. There you can check 500 important question is there. That is very much important question for the point of view of exam. I just make as short as possible. Like I can give you more question, but I thought I will give you a very less selective question I arranged and I gave in this app material. So you need to complete this 500 important technical question. Likewise question you will get in that material also. Apart from that, ebook is there. In ebook also you will find, after your subject, that communication system, after communication system short notes, you will get communication related MCQ that you need to practice. Okay, so after that mock test is also there, that you need to cover. So this thing you need to do. Okay, so those who have taken, just cover after this class, just go there and complete that question from ebook and this 500 important question. Okay, all right. And now those who haven't taken, for them I am just telling this thing. If you are preparing for BL Probationary Engineer, you can take this app material from the Mann Maker app from Google Play Store. This is my logo. You can just search there the Mann Maker, you will get this one. You can download that one. Here you are going to get one ebook. There you will get subject wise notes or key point only, and subject wise MCQ with detailed answer explanation. Then 500 important technical question is there with detailed answer and explanation, and related mock test series is there in this section. Then 150 non-tech question is also there, that you need to cover with the answer and explanation is there. Then related test series is there. Then 5 full mock test series is there. In that you will also get important question that you need to appear. Apart from that, you can check previous year question is also available there. 2023 and 2025 paper for electronics, it was there. And interview question and answer is there. So if you want this thing, just go and download this one, get from there, and my number is there. If you have any kind of doubt, you can ask me. And classes is going on in YouTube for all the branches, and this thing is also available for computer science also, electrical also, and electronics also. Okay, so those who are preparing, just take this one and prepare like that question. Like that question you can expect in the exam. Okay, so that's all. In the next class we will come with a next subject. Okay, thank you.